वेरीफाई लास्ट टाइम रुक गया था.
सर ऐसे इसमें भी रिकॉर्ड कर सकते
हैं. ऐसे ठीक है. Right. So we have done the basics of Fourier transform, right, from a graphical perspective, and we have also connected that to the eigenfunction perspective of Z and Laplace transform. Today we look at some rules of thumb related to Fourier pairs. Yeah, last time we did some Fourier pairs. Pairs mean this thing. What's the Fourier transform of a constant in time? What does it look like in frequency? What's the Fourier transform of a unit step, for example? What's the Fourier transform of a sinusoid? So in the first graphical intro we saw some of those already, and then in the last lecture that we did, we solved some of those mathematically also. Yeah. So today I want you to have some rules of thumb in mind that are useful to practitioners. Yeah. So har dafa you don't have to go back to the formulas and do all that. Yeah. So what are the what was Fourier transform, by the way? कोई जल्दी से बता सकता है graphically? Cake याद है आपको? Ugly cake. Right. So what was it? You have a time domain shape, right? You want to recreate this shape, but the only thing you are allowed to use are pure sinusoids. What do pure sinusoids mean? Their amplitudes are neither growing nor decaying. Yes, you can only play with their frequencies, you can play with their amplitudes, but only once. एक दफा आपने set कर दिया, then you cannot let it decay or grow. Then it becomes, if you allow that, you are working with Laplace transform. उसकी अपनी domain है, फायदे हैं. This is more simplified version. And we looked at, okay, you want to bake this cake. How do you bake it? You need 3 of these frequencies. If you sum them pointwise, they will lead to that shape. And you summarize this information in the form of a spectrum or Fourier plot. Yes. And then in the last lecture, we looked at how do you actually find these things. Remember, we talked about here. I have just skipped this part, right? I did not tell you how I got this answer. To get this, I need, let's say, frequency 5 Hz, 10 Hz, and 15 Hz. One of this, 0.5 of this, and point. How did I get it? That is the Fourier transform. Once you solve it, this information, this x omega, if you plot it along frequency, you are actually plotting that thing. So that is the mathematical way of finding it. Yeah. So today, as I said, we just go to some rules of thumb. Firstly, let's start with some very basic Fourier transform pair. We did cosine last time, or sine. Now, if it is sine, what do you need to create it? Yeah. Remember, Fourier transform works with what? Complex sinusoid. Okay. So to form a sine wave, Euler identity tells us you need 2 complex sinusoid. Formula देखें ना maths में. It's saying by the mathematics we know that it is this e j omega t and e minus j omega, not t, omega t. So you need omega and minus omega, 2 of these. And why are the signs opposite? Because there is a minus here. For a cosine, Euler's identity says it's 1 by 2 e j omega t plus e minus. So you get 2 peaks like that. Okay. So what about a constant? This we have seen before. We solved it last time mathematically also. It makes sense, right? To make this constant, which frequency do you need? 0 frequency. Iski 0 hai na frequency. So that's what Fourier is telling you. Even without doing any mathematics, you should be able to judge that I need this frequency here at 0. Okay. So rule 1. As frequency increases, the Fourier transform peaks move outwards away from the origin. So what's the frequency of this DC component? 0. So the peak is at origin 0. Now this guy has slightly higher frequency. This is 0, but then there is some frequency here. So the peak has moved away from the origin. It's moving outwards. Yeah. What happens here? It's gone even further outwards, and here it's gone much more outwards. What does that mean? It makes sense, right? To make this pure frequency, which is higher than this one, definitely you need a higher frequency that is here. So the peaks move outwards. So the first rule of thumb, as frequency increases, the Fourier transform peaks move outwards. Okay. So we will see how to use those also. Second, damping causes spread. Okay, damping in time domain causes spread in the frequency domain. What does that mean? Notice. Now, is this damped or is it not damped in time domain? This one. डैम्पिंग क्या होगी? ऐसे होगा ना, है हो रहा है ये डैम्प? नहीं हो रहा. तो इसकी पीक दें बहुत शार्प है. इट्स एक्चुअली अ डेल्टा. The sharpest it can get infinitesimal, yeah, or infinitely thin. Yes, that's delta here. But notice, if we replace this by a damping thing, a damped one. Sorry, pointer बड़ा करें कैसे होता है? इसका कोई है? Wait. लेजर पॉइंटर ले रहा था. अच्छा, सॉरी, वो मैंने दूसरा लिया. Right. So now imagine if this were damped, what would happen? Very interesting result. Notice, if this real thing was damped, this peak is no longer sharp. It becomes spread out. रहती वही है mostly. So उसका center है वो वही रहता है. Yeah. But then what is it doing? To create this thing, you don't just need DC at frequency 0. You need other frequencies also. ये सारी अब आपको चाहिए, ये जो इसकी रेंज में आती है ना, सब चाहिए. बट हाउ डज इट लुक? ओरिजिनली विदाउट डैम्पिंग द पीक्स आर वेरी शार्प, क्रिस्प डेल्टा होती है. एज यू इंक्रीज डैम्पिंग और एड डैम्पिंग दे बिकम broadened. Okay, so later on in some courses and in your actual work with a lot of different fields, you will actually use these results. बार बार आप फॉर्मूलों पे नहीं जाएंगे. Yeah. Notice what happens to a sinusoid. If I just look at the positive, by the way, it's very common to just look at the positive half of the spectrum. Okay, अक्सर negative is a symmetric or anti-symmetric. So notice, is this damped? No. Peaks देखें sharp, दो deltas है. Yeah, we actually calculated that. For cosine we got 2 deltas last time. So what happens if I now damp this guy? ये डैम्प्ड है ना, एनवेलोप आ गया उसके ऊपर. क्या हुआ? पीक वही है, ओरिजिनल उसका वही है, बट नाउ इट इज स्प्रेडिंग. यस, ओके. क्विक क्वेश्चन, व्हाट वुड इन्फिनिट डैम्पिंग लुक लाइक? एक्सट्रीम डैम्पिंग बढ़ती जाएगी तो ये पीक को क्या होगा? व्हाट विल हैपन टू द पीक? इट विल गेट इवन ब्रॉडर. सो व्हाट वुड बी एक्सट्रीम डैम्पिंग इन टाइम? हाउ वुड इट लुक?
So the exponential function is
एक लाइन रह जाएगी, impulse. Yes. If the damping, this is some damping, then this is more damping, then this is even more. What is almost infinite damping? वहीं पे वो kill हो जाएगा, right? So it will look like a delta. Now as you are increasing the damping, this is becoming in time more like a delta, but in frequency spreading and spreading और क्या हो जाएगा? Straight line हो जाएगा. Yes, and I have shown you and told you this thing applies both way by duality. So देखें delta का straight line है. Yes, so all of these come together actually eventually. Third rule of thumb. Okay, rule of thumb पता है by the way क्या होता है? Something that practitioners use as a guesswork. Yeah, ऐसे देखिए. Okay. या जैसे वो आप लोग फोटोग्राफी वाले वो rule of thumbs होगा I guess. This is rule of thumb. Yeah. So third rule of thumb, sharp changes. Yeah, I mentioned this before, but sharp changes or edges require a lot of frequencies. Now notice here, no sharp changes in time. Yes, no sharp changes in time. Even slow change be needed more frequencies than the slowest change. Yeah, but if the change is extremely sharp, ये तो बनाने में तो at least infinitely drop हुआ है वो. Yes, then you will need a lot of, ये actually doesn't stop here, it keeps on going. Yeah, that means you need all these frequencies in this much amount. ये height बता रही है कि उस frequency का कितना amount आपको चाहिए होगा ये बनाने के लिए. Similarly, if it is a repeating pattern here, you will get something like this thing. Yeah, so it keeps on going. Basically that means the sharper it is in time, जितने edges ज़्यादा होंगे signal में उतनी ज़्यादा frequencies आपको चाहिए to create it let's say most accurately. But usually we stop at some point. We say okay, this much accuracy is enough for us, so then we stop there. Yeah, okay. This is again the same thing, but now what is the most extreme sharp thing? It's the delta in time. So what happens? You need all the frequencies. It keeps on going. Yeah. So this is another way of reaching the same conclusion. Fourth, periodic functions have discrete spectra. So if your function in time or signal in time is periodic, okay, that can be square periodic, triangle, or a sine wave, whatever. If it is periodic, then its spectrum will not come out continuous, it will come out discrete. Okay, and this kind of leads to the concept of Fourier series. Okay, I will not cover in this course, but just so you know, Fourier series is nothing special. It's just because these are now discrete, you can look at it as a series, not as a continuous variable. Okay, it becomes a discrete variable. When does Fourier transform become discrete? When the original signal is periodic. Okay, so नोट करें जहाँ पीरियोडिसिटी नहीं थी, नोट करें कहाँ पे, कहाँ नहीं है पीरियोडिसिटी. दिस इज नॉट पीरियोडिक, राइट, इट्स डिकेइंग एंड एक दफ़ा ही हो रहा है ना, क्या, नो रेपिटेशन ऑफ द डिके प्रोसेस. सो नोटिस, इज दिस डिस्क्रीट? ये तो कंटिन्यूस एक जा रहा है, कंटिन्यूम है, यू नीड द एरिया अंडर दैट थिंग. या, सो सिमिलरली हियर लुक एट दिस, दिस वाज पीरियोडिक square wave है ना, square wave, periodic square wave. Look at the Fourier transform, it's discrete. This is not periodic, it's a single square wave. It's not a single square wave, it's just a single pulse, repeat नहीं हो रही है. तो उसका look at its Fourier transform. This is a continuous function, पूरा continuous चल रहा है. Continuous और discrete तो याद है ना अब तक, decided by the x-axis. Yeah, so again over here, rule 4, periodic functions have discrete spectra. Sometimes we call that the Fourier series, but with some additional constraints. Fifth one, well, it's not really a rule per se, but it says that multiple effects can be combined. तो पहले चार आपने पढ़े हैं ना, you can then try to see them in action together. Yeah, which ones do you see in action here? क्या क्या नजर आ रहा है आपको इसमें? इनको अगर आप कंपेयर करें, ये this is time, this is its Fourier transform. This is in time, this is Fourier transform. This is in time, this is in Fourier. Which effects do you see here?
सर जितना वो close हो रही है हार्मोनिक्स उतना वो दूर जा रहा है.
Yes, so as the frequency increases, the peaks move outward. That was our rule of thumb number 1. Yeah, और कौन सा नजर आ रहा है इसमें?
So damping जितनी ज़्यादा हो रही,
Damping. What's happening with the damping then?
ज़्यादा
If it is damping is increased, the spread will increase, right? अगर इसमें body or damping. let's see if they are actually damping or not. इस case में तो ये damping, I think they are showing the same amount, but notice since they are all damped, it's not a sharp peak. Yeah. और कौन सा rule नजर आ रहा है इसमें आप?
periodic functions.
Periodic है या नहीं है? नहीं. Yeah. It may trick you into thinking कि चूंकि वो साइन वेव चल रही है, लेकिन पीरियोडिक फेज की एग्जैक्ट वैल्यू आनी चाहिए. या एग्जैक्ट तो नहीं आ रही, पीक्स तो रिपीट हो रही हैं, लेकिन हर दफा पीक फ्रॉम द प्रीवियस पीक इट हैज अ लोअर मैग्नीट्यूड. अगर if it had the magnitude been same, then you would say it's periodic. So it looks periodic because inside there is something going on that's periodic, but overall it's not periodic. That leads to, notice this is not discrete, this is a continuous spectrum. Yeah. Good. Rule 6, I've already mentioned duality. Okay. If a certain shape in time leads to a certain shape in frequency, and if you change the labels, the answers will still hold. So if you replace xt by xf and f by t, just replace the whole thing, the answer will still hold. This is called duality. Okay. So if a constant in time leads to a pulse or impulse in frequency, then an impulse in time leads to a constant in frequency. Okay, so this is duality. And Dubara, quickly, what were the 6 rules we looked at? Rules of thumb. First, what is it? As frequency increases, the peaks move outwards. What's the second one? Damping causes spread. What's the third one? Sharp changes require a lot of frequencies. Fourth one, yes, periodic functions lead to discrete spectra. Okay. Fifth, effects can be combined. Sixth, there is duality in time, and this is not only true for Fourier; it's also true for Laplace, okay, and Z also actually. But some of them you may have to skip. Right. So I think that's it for today. मुझे बंद कर ले